These are the notes for LT4 in the space science unit, and the title is projectile motion, but the task is to apply the independence of x and y components of motion to projectiles both on Earth and then in space. So a couple things to look at. First, the x and y components. Think about the graphs that you've dealt with both in math and science. So we know the x-axis is the left and right one, the horizontal, the y is the up and down, the vertical. And that's the same thing when we talk about projectile motion. So we're looking at the left and right, and we're looking at the up and down. We're looking at how, even though they're independent of each other, so x does not depend on y, nor does y depend on x, they both contribute to the shape of a projectile's path. All right, so let's start at what a projectile is. So just the basic definition of a projectile is an object moving through either the air, let's say if we're on Earth, or the vacuum of space. It could be, heck, a shooting star entering Mars's atmosphere. All right, so bottom line is it has to be something that's in motion. So a bullet, when it's traveling through the air, like in the bullet fired versus bullet dropped Mythbusters that we watch. It could be a baseball, as long as the baseball's flying through the air. Okay, it can't be when the baseball is in the catcher's mitt, let's say. All right, it has to be moving through a space. It could be, oh heck, what else could fly through the air? Maybe you toss a rock. All right, you toss a rock towards a pond or something like that. Okay, all of those things is an example of a projectile. All right, so the reason we care about these things partly is because of the path that they take. And when we're in a space science unit, we're going to be looking at planets very, very soon and looking at why are their orbits either circular or elliptical, because a planet is just a big old projectile. Technically, we're all a projectile because we're on the Earth and it's hurtling around the sun. Okay, so let's look at what is called a parabolic trajectory. It sounds very fancy, okay, but most all of us in math class have seen one of these before, and we know that's a parabola. So the trajectory must look something like that. Use your imagination, pretend that that's a perfect drawing. We know they never are with me. But trajectory just means the path. And the path is composed of the x component and the y component. Okay, the x and the y. And we already said these two do not depend on each other. They are independent. All right, they are independent of each other. So x and the y component. So our x is left and right, horizontal. Our y is up and down, vertical. So let's think about this. Right, if you're in class, we do lots of demos. I throw a ball around the room. But just think about tossing a ball straight up in the air. If we toss a ball straight up in the air in this direction, it only has a y component. If we take a ball and we throw it perfectly horizontal, okay, now we got to pretend there's no gravity, and that's not real. All right, but anything horizontal has a lot of x component, but less y. So what we say is in the x direction, there is zero acceleration. Because think about that. When you kick a soccer ball, once it has left your foot, there's nothing pushing it along if we ignore air drag. There's nothing slowing it down in the x direction if we ignore air drag. Once it leaves your foot, it's gone, right? You can't bring that back. Once a softball leaves a bat, it's gone. You can't bring it back. But for a y component, it's always there. Okay, gravity is always there. If it's on Earth, it's always about 10. Okay, so in the y direction, we always have an acceleration. If this is a football at kickoff going up in the air, gravity is slowing it down. At the very top, it only has an x component because gravity is starting to speed it back up. So gravity is going to accelerate it down this way. So it slows it down as it goes up, it speeds it up as it comes down, but always at the 10 meters per second every second. So if we do a drawing that will kind of hopefully help make this make sense, even if it is my drawing. And you've got a person Let's say that it's a 0G environment, so absolutely not realistic, no air drag. But think what would happen if they were able to hurtle a ball straight out in front of them, okay? And so it only has an X component. You would see that ball travel in equal increments in the X direction in equal time intervals. So at 1 second, you would see it here. It's left their hand, so it can't speed up, it can't slow down, there's no gravity. Okay, so you would see these same distances all the way across until it hits a wall or something like that. Now we know that doesn't happen, but we see something similar to this, we just don't know it. Now as soon as the ball leaves the person's hand, in the Mythbusters episode, you need to watch it on Moodle if you haven't, in the Mythbusters episode, after 1 second, what we would find is a bullet would drop about 10 meters. Okay? Or this ball, once it leaves their hand after 1 second, sure, it's traveled here, but it's also started to fall. And after 2 seconds, it would have dropped even farther because gravity is bringing it down faster and faster and faster. And after 3, maybe it's down here. And after 4, it's here, and I've ran out of space because I don't have good spatial orientation, all right? But you start to see this parabolic shape as an object falls. And all it's doing is falling under a straight line path of where it would be without gravity. Okay, that's where the parabolic trajectory comes from. So let's kind of put that into numbers. After 1 second, it's dropped 10 meters, and it will be traveling 10 meters per second. After 2 seconds, it would drop an additional 20, right? Because it's going 20 meters per second now for a total of 30 meters, and it's going 20 meters per second. And the distance part isn't as important as long as you understand that it falls a bigger chunk of space up and down, because it's going 30 meters per second. So it would drop an additional 30 meters in that one. And then the fourth one, 40 meters per second, 50 meters per second. So if you jump off of a table in a classroom, it's not recommended, but you're probably going to live through it, right? You jump off a building's roof, you might not, because the longer you fall, the more distance you're falling per second, then the faster you're going to hit the ground with. All right, so don't become a projectile off of a building for me, all right? So we get this parabolic shape. So even though it's a combination of X and Y, okay, both of those contribute to the shape. No, the amount of wind, let's say, doesn't dictate the drop, right? And the drop doesn't dictate how fast the ball goes shooting out, or in Mythbusters, how fast the bullet went shooting out. So even though they combine to make the shape, they do not depend on each other. They don't really have anything to do with each other directly. Now, depending on why you're watching these and what days you've missed, that sort of thing, we go through this. There's a simulation, and you get to it off of Moodle. So it would be in this unit, so the space science unit on Moodle. And you'll see a cannon. It might be a good idea to load this thing up and kind of see what does happen when we have air drag on, what happens to the shape of the path, that sort of thing. All right, this is obviously for a class that's happening right now. And that is it for LT4. Good luck.